Okay. Nobody breathe. I will end you. All right. So, we're supposed to end at 8 o'clock. That gives me half an hour. No, I will not. This presentation was developed originally as a result of looking at failed presentations on this topic. 4 of them, as a matter of fact. And the number one problem that we had with people walking out going, I have no idea, it sounded important, but we really don't have a clue what you just said, was an attempt to pack far too much information into the allotted time. So we reduced it down, and we covered a subset of topics. So, if I run out of time tonight, I will simply stop. And we will have had a good presentation on as many topics as we got through. But I'm not going to try and push it all in.
We'll have you again, Stephen. You can come back as many times as you want.
Ah, wonderful. So,
the irony.
This presentation I gave last year, Computer Science for the G Programmer. It springs out of an idea that some of you know Dimitri. He's a CLA over in Europe. Several of us have had. There's this body of knowledge that exists in computer science, programming domain, software engineering, that is very useful for LabVIEW programmers to have. We don't like them to have it, you know, specifically for getting up off the ground, for doing their initial connection to their measurements, for doing basic testing work, initial prototyping. But at some point, when you start deciding to do applications and reusable libraries and deployments and the you know, all-important second test system that's going to run in parallel, suddenly some of these things start becoming more important to understand. And so we wanted to find ways to restate them in terms of experiences of LabVIEW engineers as opposed to the concepts as they usually come to us, which is packaged in terms of void types, procedural languages, and a lot of abstractions that don't necessarily apply directly to LabVIEW. So when we talk about LabVIEW, we've got this massive amount of power, and we package it down, and we try to bring it to, well, to the masses. As one of my coworkers once joked, LabVIEW's job is to put all the developers who work on it out of a job. Because, you know, at some point we'll be able to all write in LabVIEW, and then nobody will need us to do it because you'll just extend LabVIEW. But as it stands, we haven't quite mastered the technology to bring all of that down. And so at some point, having the training kicks in and becomes valuable again. That's what we're going to try and get through today, is one particular set of values. These were codified in the early 2000s as fundamental principles, things that you should aim for, utopias that can never really be achieved, but that affect every software design decision that you make. And I am vaguely stunned that this list of 5 has not been extended to 6 in about 10 to 12 years. These 5 principles, if you keep them in mind and you regularly ask yourself, have I at least given them a little bit of thought in the design of this piece of my software, do an awful lot to turn your code in a good direction. As I say, they're not really achievable. These are, every single one of them comes with caveats and times when you're not going to be able to quite achieve that ideal. And all of us work in real-world domains where business pressures are going to say you're just not going to take the time to do that extra length. But you want to think about them, because every time you decide not to follow one, it generally means you've generated technical debt. It generally means that the next time you're asked to upgrade something, or the next bug that you have to track down, will have incrementally harder time doing, and thus more time. Now, these apply to every software engineer you write. These are broad principles that we're going to talk about today. Functions, classes, libraries, modules, applications, distributed systems. Every layer of it, these come back into play in different forms, different reflections. So SOLID is an acronym for these 5 principles, and they're all ridiculously long named, which is why it's lucky that we at least have SOLID to get it down to manageable. But they're well named, and they're uniquely named, and conveniently they all have 3-letter acronyms. So today we're going to talk about SRP, and maybe we'll get to the other 2, OCP and LSP, before the evening is out. Every one of these can be a semester. There are dissertations written on all of these. Professor Liskov of Liskov Substitution Principle, she got her PhD for that one. So there's a lot of ground you can tread over here. So this is a high-speed summary of all 5. Entities, the single responsibility principle says that an entity should have one and only one job. You all get stressed if I try to give you too many jobs to work on. You can't task swap, you can't work, you make mistakes, you do the wrong thing, you try and put things in the wrong place. If I give you one assignment and tell you to just go do it, you do a much better job. Works the same for software. Don't know why it's not exactly a sentient entity, but perhaps it's because of the sentient entity that's behind that code that's having to tell it what to do. The job should be describable in one sentence. It may be a very complex job with lots of moving parts, but get it down to one sentence. The goal, the reason that you try to do this, is to make the code base learnable and maintainable. If I can point to a module and say, what does that do, and you can answer me briefly, I have a hope in Hades of figuring out which is the moving part that I need to make stop moving, or vice versa. For classes specifically, they should do at most this one thing, and you should be able to point out the 1, 2, or 3 primary methods. Do. That's the core method of this class. Start, stop, good one. Set up, execute, tear down. These are examples. Classes that get far beyond that, they may have support routines for those 1, 2, or 3 methods. But if they get too far afield, we'll see that they start falling apart. Open-close principle. Entities should be open to extension but closed to modification. What that basically means is you should write your software so that you can plug in new extensions and you can make lots of things expand and grow by feeding it things rather than going in and modifying its inside. You want to give a connector pane on your VIs where every terminal you could possibly imagine can be applied from the outside so that you never have to modify the internals of the VI again. Now, all of these principles stack in different ways. So we don't ever want to do that to such a degree that we violate single responsibility principle. But as we'll see, there's a way to extend these things without creating these problems. The goal is so that after the first release, no new features are ever added to the core code. This has been signed off on, it's been vetted, tested. Your FDA, medical practitioner, nuclear regulatory agency has approved it. It shouldn't be touched again. And the more you can simply add to it, slot into it, the better. Liskov substitution principle. Inheriting entities must maintain parent invariance. A better way to say this is keep your damn promises. If a parent class says, I am always going to do X, I will never do Y, and I will only do Z on Sundays, the child class had better keep every single one of those promises. If you ever have any promise that is made by the parent class that the child class does not keep, then there is some caller somewhere who is depending on that promise who will be screwed up when you try to send your child class through their framework. Now, the great part about this is there's a mathematical proof that you can never actually achieve it. That's Liskov's PhD. Any system you write, any piece of code you write, the parent class will make promises that you never even thought to write down in the documentation. We may get to some of those today, but it's really great. You can't ever achieve it. You are guaranteed to be screwed. This is the way software works. Liskov substitution principle. If it looks like a duck, quacks like a duck, but it needs batteries, you probably have the wrong abstraction. Interface segregation. Many context-specific APIs are better than one general-purpose API. You have lots of things. Get lots of things. Get the tool that does this job, and the tool that does this job, and the tool that does this job. Don't try to get the one tool that does everything. So we covered this one in this year's NIW conference. Dependency inversion. Depend upon abstract entities, not concrete entities. As much as possible, try to write an API that does as little as possible, but has plugins to plug in the concrete behavior behind it. Write your color code to talk to those interfaces, because the interface can be frozen while the background changes. Again, this one I went through in detail at this year's NIW, which you missed, but which Mark Balla videotaped somewhere. So that's the high-speed summary. Now, I crammed all 5 of them together because every time I try to give this and I try to skip and I just say, oh, well, we're only going to talk about 2 of them, everyone's like, but I really want to know what the others were. And I say, read Wikipedia, and they say no. So that was the 5-minute summary. Now we're going to slow down. Take a deep breath. There you go. And we're going to go into the single responsibility principle. Single responsibility principle says, do one thing, do it well. You should avoid things like mother clusters. Some of you may have heard this term. It's the cluster that doesn't fit on a screen where you've turned on the scroll bars in both directions, and you have documentation off to the side that when printed out is a small novel, and you really hope that it's at least as exciting as War and Peace. It never is. It's the VI that spans multiple screens. Did you know that there's a limit that you can only nest 219 structured nodes in LabVIEW before LabVIEW crashes? I got that car. I felt so sorry for that man. I fixed that bug.
Why?
Oh, no, just so it doesn't crash anymore. It cuts you off now.
Okay.
Yeah, it now cuts you off at 36,000 pixels.
But he has bigger problems at that point.
Yeah.
Yes, he does. The biggest problem is that their code works. That's the hardest thing. If the code stopped working at some point, you might be more inclined to give it up. But the fact is that they keep being able to band-aid it. You've all seen the monolithic device driver, the one that supports everything. It has an API that you, okay, do I need this function? No. Oh, I need this one with this set of parameters, and GPIB is my favorite example of this. Strings that are arbitrary, and people just add another one, and it all goes through the single one-node interface that is send command. If you have this pocket knife that unfolds and does everything, you frequently cannot find the one tool that you actually need in the mess. And if you've ever tried to hold a Swiss Army knife to actually do some fine cutting, I guarantee that if after an hour of cutting something, tomatoes or whatnot, you will be begging for a good cutlery knife.
And the screwdriver on a multi-tool kind of stuff too.
Yeah.
I'm sorry to interrupt, I know.
Yeah.
But like, for example, on the single responsibility, so one thing that I see a lot is the huge cluster that has like 60 elements in it, because it's so handy to have everything on that wire. And then you go into the VI and they're just an unbundle of 2 elements.
Yes.
So would this be an example of the...
It can be. More often it's, you should have unbundled it on the caller and sent them only the 2 that they needed. Sometimes it's just a failure to recognize that single giant cluster is actually multiple smaller clusters that should be traveling on parallel wires but not actually a single cluster. You generate huge amounts of data copies that are totally unnecessary when you start routing this single thing to everyone. Sometimes it's just not recognizing that it actually can break down into a class with a decent hierarchy and you're actually supporting the union of all possible functions in there. So, the virtual instrument C++ class. So, LabVIEW is a piece of software, therefore it's written in a programming language. Weird how that works. And we have a class called virtual instrument, which we are in the process of refactoring. After 30 years, LabVIEW is having its midlife crisis, and it seems like it follows the single responsibility principle. This class represents a virtual instrument in memory. You all know what a virtual instrument is. It's got a front panel, it's got a block diagram, you can run it, you can edit it, you can save it, you can load it, you can do everything to it. And so it has developed methods: load, mutate, save, for previous, for future, that's not released, compile, run backwards. No, not really. But I do get requests for that. Rename. They want, I want to put in outputs and have it go backwards to figure out what the inputs were, so people can test and generate test results. Anyway, feature requests are cool because honestly, if I could have figured out how to do that, would that not be neat? See, sometimes I actually have to spend about 5 minutes going, is that really as insane as it sounds? Because wouldn't it be useful? Anyway, it has developed, and I kid you not, I think I have got my hands in the actual correct position at 10-point type, the list of functions that Virtual Instrument has on it. It's quite extensive. It has 7 32-bit flag fields of Boolean states that you can toggle on and off depending on its various conditions. Is it running under RT? Does it have open when called on it? Does it have close when finished set on it? It's amazing. It is awe-inspiring. It's being refactored. It's being divided into the proper pieces. If this is a runtime virtual instrument, this is an edit time virtual instrument. This is the various pieces that we've kind of about. We've been working on this refactoring now for a couple of years. We're trying to get it down to the point where we can point to it and say, this is the focused task that this particular entity does, and it properly marshals information to the other entities so that you have the edit model, and when it's time to run, it will generate the appropriate running model. And the running model doesn't have all of the overhead of the editing model, and it's a much more stripped down basic piece. Some of you may have seen size reductions in LabVIEW 2015 of the in-memory, the in-memory footprint and how much space things take. A lot of that is because things are no longer having to replicate a whole bunch of information on clones that they didn't have to, stuff like that. It evolved over time, and it is so easy to add one more feature. I need to print a virtual instrument. Printers have just been invented. It's 1990 and we have color. I'll just add a print method. Because that's what it needs, right? It's the right object. It's got all the data. I just need to print. I should put a print method on it. And the temptation is there. But as time goes on, it becomes harder and harder to add features. Until you reach my all-time favorite bug, Guy added the ability to set the background color or the background image of a VI and broke dynamic dispatching.
What?
How does that happen? Those aren't even... You did what? I couldn't talk for about an hour as I just stared at the code as I realized which change set it was that had actually broken all of LabVIEW classes was setting the background image of a VI. And it's because he had accidentally stepped on a set of flags fields. He never intended to actually really be touching. He thought they were unused, so he reused them for his project. Whoops. So, thus began the untangling of these things. And it's not just a problem for you as the person who owns the code. I'm the developer. I have to worry about accidentally breaking some other feature because of this monolith. But really, does it actually affect you guys at the end? I mean, that's why managers push back on this. Oh, we don't really need to refactor it. It works fine for customers. Yeah, you're having to stress harder over getting all of this right and being extra careful and all that, but that's what I pay you for, is to be aware of semicolons and wires that are, placed with 1 pixel accuracy and all of this. That's your job, so why would we refactor just to make your guys' lives easier? But it has an impact on your customers. It has an impact on my customers, which is all of you. You can't edit a VI while the VI is running. Why? Because that's the same entity. We don't have a separation of the edit VI from the run VI. We don't generate one from the other. Reentrant clones used a lot more memory if you go back a couple of versions. Back around LabVIEW 2011, there's a lot more memory every time you created a clone, because they were carting around the entire block diagram every time. They don't need to replicate the entire block diagram, but they didn't know how to operate without one. We've slowly over time reduced all of this stuff down and made it so that things are properly instrumented to the point where this has one responsibility, this has a different responsibility. Print is still on virtual instrument. Serialization. I've been told that nobody knows what serialization is. It means flattening and unflattening from strings. Whatever your file format, whatever your data, serialization is the process of going down, deserialization is the process of going the other direction. This is a subtly hard problem, turns out. Most people are like, yeah, you turn it into a string, you read it back later, and why is this difficult? But so some of you may have seen my giant library of 800 plus VIs to serialize and deserialize classes, and it handles everything. It's really awesome. It's just a beast. Yeah. So JSON, XML, binary. Which format did you want? Okay, well there's a subset of VIs.
Mutation. Oh, God, we changed our version. Well, we're going to read the old file formats and the new one. Save for previous, because, well, now that we've read the old one, we actually need to send it back to the other guy because the server revved, but the client didn't. Class renamed. Oh, the data comes in and says it's this class that no longer exists. Oh, well, that's because it's this other one over here. Dispatch tables don't even work at that point. You're trying to name match and things. Different human cultures. Whoever it is that decided the Brits get to use a comma and we're using a period for the decimal point. And there is one true timestamp format.
Nope.
Cultural hegemony. I didn't used to support it. Mini languages. These little tiny expression languages. Like, okay, I've got this vector graphics thing, and I could write down all of the fields, or I can express a little mini language that is like your old logo commands of move to this point, drop pin, move to this point, lift pin, move over here, and you end up with this nice, elegant little string that's easy for humans to go in and type into, but now you've got this custom parser just for that one type thing built in somewhere into your monolith, and it's a special case everywhere. I'm only looking at the serialization. I'm not even going to talk about the deserialization, because that's an even harder problem. So the obvious option, if I need to handle flattening and unflattening of I've got some class. I want to save its data. I'm going to flatten it. I'm going to unflatten it. The object solution, I'm going to add a to string and a from string to my class. Great. One of the input parameters is going to be its file format. And then I'm going to have an input parameter for the decimal point character. And then I'm going to have an input parameter for the version, because my objects have versions over time. And there's probably a lot more, but that's enough complexity for tonight. So, we build this. We have this case structure here that says, okay, we're going to go to the XML. And we have the escape characters command for XML, because you got to put in, you can't have an angle bracket anywhere in there, or you confuse everything, because that's your delimiter. So you got to escape that. We've got, we definitely should have a sub-VI here, because this is the actual code that we're going to use for building an XML string. Probably going to use that in a few places, which means if you put the actual code right here, we're taking that digital data and transforming it into a string. That would be putting all of the code for waveform right here. And somewhere else, you've got a bunch of code for waveform. And that would be getting away from what this guy's job is. This function's job is to serialize that object. That is the one job this VI has. And anything on his block diagram that isn't dedicated to that one task is probably something that should be offloaded to a sub-VI. So the act of turning the digital data into a data type that we can actually flatten, that should be offloaded. That's an easy one to spot. When your diagrams start bloating and you start circling regions of your code and going, this part handles this, maybe you should make a sub-VI that handles that and put that in the context help. I haven't even used these parameters yet. I just used the first part just to kind of show you how things get started. And it gets a lot more complicated if you start going down this road. Because this is the job of this one VI, is to flatten this class, but he has to take into account all of these other things and handle all of these cases. All right. So let's say that we're going to split the world into two classes. We're going to have one class that is the class to be serialized. His job is not to produce the string. His job is to state the data that needs to be flattened. I am the object. I have a list of attributes that are the important information for me to save. I put them in some standard data types, and I hand them off. It is not my job to put them as a string. I simply give Alan a list and say, this is my data. Here's an integer and a float and a timestamp with the right sequence, and a few other pieces of data. There you go. I'm done. Now, he is going to be the second role. The actual string to and from the work is going to be the serializer class. Totally different entity.
And his job is to take this list of data, he doesn't really care where it came from, he's got a standard pattern of data, and make it into a string. We can have inheritance to create different child serializers. So we can have an XML serializer, we can have a JSON serializer, we can have a binary serializer, we can have a throw it in the trash and do nothing with it serializer if we want it. Those are actually useful sometimes. And whatever. These things, flatten it, our job is to actually put that data into a particular format. We segregated those responsibilities out. We divided the world, and we said, you focus on one thing. Don't try to do my job. Don't try to do his job. Do one, and do it really, really well. The nice thing about software is, unlike human beings, where every time you hire another person onto your team, you have to pay them more, software objects are generally free. You can create another one, and instead of putting more work on the one that you've already got, and the cost of the code is the same. In fact, sometimes the cost of the code is less. And if anybody figures out how to do that with human beings, I really want to know, because I could use a few more interns. Now,
That's what factories are all about.
yes, the factory pattern, we tried to use that on interns.
Well, that's what manufacturing facilities where you give everybody a single job, you
Oh,
pay them.
yeah.
then-
That's true,
then
too.
the guy who knows how to put the entire car together.
So, we're going to have Serializable. That's the name of the class. He's going to go to string. And his toString is going to repeatedly call serializer add item. So, I need to serialize an integer. I'm going to call the add integer function. Hey, add this integer. Okay, now add this timestamp. There we go. And we keep going. And he eventually writes down the whole string. So the result, by separating the responsibilities, we have independent variants. We can change the serializer. I can say, I'm done with Alan. I don't need any more XML. I need JSON, Damien. All right, here's the same list. I don't have to change my work. I just talk to a new person, and he writes down a totally different string. So we can change the encoding without having to change the original class. We can fix the human language problems that are, or the escape character sequences. All the work needed to do XML escaping, Damien doesn't know anything about it. He knows about the JSON escaping. This is all divided up. JSON's escaping, yeah. Sorry. So this sort of dividing up of labor and getting to the point where you can have true flexibility is what the AQ character lineator does today. Now, remember, we're not talking about deserialization, so there's a fourth part, but we're not talking about it. For the AQ lineator today, I actually split into three major pieces. The serializable, that's the data that you guys produce. You inherit from serializable, and you say, I am data that needs to flatten. The serializer, that's the guy who says, I'm in charge of the main protocol format. And then the formatter, and that is culture specific. That's the British format versus the American format for decimal points, or the Roman numerals for integers, or whatever else you would like to plug in for your particular culture that is going to then fit into the protocols of JSON, XML, binary, etc. Each of these has a tree of child classes to do one flavor of that specific task. I think I'm actually just broke 900 VIs with the last feature add. Have I gone far enough? Well, no. You see, there are different ways of being flexible, and the Serializer class currently says, I take data values provided by the serializable and format them into a single string. Great. One focused feature. The code has been very easy to maintain. I wrote 900 VIs in the space of a month, and they almost all worked on first to debug, because each VI is very tightly focused. When you get a blank slate engineering and you can really apply this stuff, you can crank through code and really generate some serious large-scale code architectures like this, because you in your own mind are never overloading your own thought processes. The trick is that this is very inefficient when we want to save the disk or stream over a network. Just because generating an in-memory buffer of a giant string, okay, I've built the giant string, now I return that string to a caller, and then the caller turns around and says, okay, now I'm going to put that into a network packet, or now I'm going to turn around and write that to a file on disk. He never really needed the in-memory buffer in the first place. So the future request is to break
output is a new class with its own descendant hierarchies, which is where the data coming from the serializer should go as the serializer produces it. So you would have a memory buffer that would produce the in-memory string. You would have a file on disk, which would be backed by a file I/O refnum and would know how to stream it out immediately, so you'd never even build up in memory. You have a network stream that I'm just pushing it out over the network as soon as parts come in. Its one job is consumes formatted strings from the serializer and outputs them to a destination, such as an in-memory string, a file, or a network connection. One responsibility per class. Now you notice, I was able to describe the serializer in one sentence, and I had nice concentrated functionality, and it didn't feel in my current incarnation like I'd overloaded it with too much responsibility. But for my future flexibility, it turned out that it actually secretly was actually responsible for one thing more than it should have been. It was actually deciding where to store the string. When I say these are unachievable goals, you can never achieve this utopia, you can't really ever enumerate all of the things that a single entity of software, be it a class, a function, whatever, is doing, unless it's just trivially ridiculous. These entities have implications. They have things that they just take care of as part of whatever it is they do. One of my favorite writers talks about implied spaces. When you build a house, you say, I want a ground floor and I want an upstairs, and there's a staircase going between them. That implies the closet under the stairs. You never intended to put a closet under the stairs in the house. It wasn't the architectural dream of, I will have the ultimate closet under the stairs. No. It was implied by the rest of your architecture. And so, as a result, it supports storage as sort of a side effect. But it's not the primary job of that architecture, but it just sort of becomes a part of it. And it becomes this extra responsibility that nobody even knew that the house was responsible for storing objects. It didn't occur to, it was supposed to be just a place you lived in. And so you have to offload these responsibilities as you recognize them. Huh?
Carlin covered that years ago. A house is a pile of stuff with a cover on it.
Yes, exactly. So you end up with these responsibilities that are hidden in your code. You don't even think of them as the thing it's actually responsible for. And when it comes time to refactor them, it's often easy to say, oh, it's already there, I'll just tweak it, as opposed to taking the extra bit of time to pull it out and be its own entity at that point. You don't have to pull it out. You can end up with a single virtual instrument class, and it works great. It's very efficient, got all the pieces, you can ship on time, but eventually the technical debt builds up to the point where someone's like, no, this has to change or we can't add the next piece.
What happened?
I have no idea.
Or did you click off of your view in the center mode?
Yeah, he's still.
There we go. So that leads to the question, can you go too far? Yes. There is a term that I am very fond of called the architecture astronaut, the person who has built the mountain of abstractions reaching to the summit, and he can no longer bear the mere air that you mortals breathe, for he has his own enclosed suit that he may survive up on the rarefied heights. As you create these ever more elaborate abstractions, and you have the entity that handles the allocation that is separate from the entity that handles the sort, that is separate from the entity that handles the copy, and you can end up in a place where everyone's looking at you going, I know what every individual one of these things does, and I have no idea how to put them together. It's a real danger. Software can go too far. How do you know when you've gone too far? Well, sometimes it's because you can't breathe, but more often it's because you're a well-trained architect and you suddenly recognize that you've just gone beyond it. But you have to have worked on a system that has gone too far before you really figure out where that limit is. So I encourage you to look at other systems, particularly if you have a really large failure at your company, like a project that just absolutely disastrously fails, but everyone was like, those were some pretty sharp guys working on it. Go study their code base. You will learn so much from those. They're very enlightening for how software can go off the rails. So, single responsibility principle. Does that make sense? Questions? All right. Is it the responsibility of this presentation to cover another topic? It's already 8:05. I can stop here. I can go on. I don't have any place that I have to be until 9, so I could in theory stay another hour, but I will not hold you here if you guys are ready to go. Yes?
For staying. Hands up for staying.
Upstairs. You live upstairs. Let me go ahead and go through Liskov. Liskov is very quick. I don't have a whole lot on this one. Liskov, keeping your promises. So, you've all built at least one LabVIEW class, right? Good. Has everyone built at least one child class? Do you know what inheritance is? Okay, I'm seeing lots of nods. All right. So the question that Liskov says is, should X inherit from Y? Is it appropriate? This Y class looks like it has all of this marvelous functionality that I want to reuse. Can I inherit from you? And it's not as hard, it's not as easy a question as it might seem. Remember the duck. We call this a duck, and we call this a duck. We put some adjectives in front of it, but adjectives in front of things are exactly what child classes are. You have the serializer. You have the JSON serializer and the XML serializer. How is that any different from the, I don't know, hardware serializer? The hardware serializer is something that takes a piece of hardware and turns it into string that you can like tie around packages. Totally different, but it sounds the same. Now, how do you know they're not related? Well, in that particular case, it's kind of obvious. I mean, everybody laughs because you're like, they're doing totally different things. But that's the trick that Liskov challenges us to answer, is what is it exactly that the parent class is doing, and what is it promised to do, and can you actually maintain those promises?
Making baby ducks versus entertaining baby.
Something along those lines. All right. So the Liskov substitution principle. For X to be a good child class of Y, then, this is where the mathematics comes in. I like this part. If any property is true of all objects of Y, then it must be true for all objects of type X. If that's true, you can inherit. And that has to be true for all such properties. Liskov proved that you can never actually prove that you have accomplished this. It's kind of got something to do with the Gödel incompleteness theorem. Any set of rules that you have around an item, there will always be an assumption that is made that is neither provable nor unprovable. There's implied behaviors. It's great. Anyway, how many of you have heard the phrase identity, state, behavior? Is this a litany? I don't usually use these in front of a lot of LabVIEW programmers. Identity, state, and behavior are the three things that define a LabVIEW class. A class has its identity. That's summarized in its name. You name the class, that's what it is. I fulfilled this role, that's me. I am a programmer. I am a father. I am a dancer. I am the garbage collector. I am whatever it is, that's my identity. I have state. I am currently the street cleaner, and I am at the Parmer and Mopac at the intersection, and I am cleaning that street. Or, I am tired and running low on energy and I need to eat. That's my internal state. I have behavior. I have things that I do. I have, if it's a meeting at 8 a.m., my behavior is to sleep through it. And if I as a parent make that promise, I expect my child to also keep that promise. We will sleep through the 8 a.m. meeting. I make a great babysitter. Identity, state, and behavior can be answered about any class. You can look at a class and say, what is its identity, state, and behavior? And then you look at the other class and you say, do you match on all three of those principles? And it's a surprisingly easy thing to mentally break down and at least pause and ask. And frequently what happens is you get two of them where you can say yes, and the third one is almost. Almost doesn't count. If you ever get an almost, you probably should do containment instead of inheritance. Now, you've all seen the private data cluster, right? You have a class, you've got this private data cluster, and it's got a list of fields. You can inherit from a parent, or you can take another class and you can put it as a member variable inside of yourself. When you take it and put it as a member variable, that's containment. That's saying, I have an instance of you. I'm not one of you, I have an instance of you. And then you might take some of its methods and create your own methods, not by inheritance, your own methods that sort of re-export that behavior. Now, this is a lot of work, and programmers grumble about it. And they say, they can make comments about, God, I'm having to recreate all of this work and these wrapper VIs and blah, blah, blah. I'm just going to inherit. And that's the easy thing to do, is I'm just going to inherit, and it gets close. When you take the time to create those wrapper VIs, you've created this little space. These blank block diagrams that only have a sub-VI node on them have lots of blank space around them. And do you know what goes in that blank space? All of the little shims that you need to take care of almost. That's where you put the code that gets the range to be actually in the range that this other class expects it to be in. That's where you put the error handling for the case that you really actually don't support. That's where you put the new error code return. Now, it means that this class that does containment, I can't pass it into a function that takes one of these. You know, this guy's this nice class, and I can pass him into the frameworks, and he goes everywhere. And if I inherited from him, I could go through all of those frameworks. But because I'm an almost, if I were to try to go through those frameworks, I'd probably break something. That's what happens. So these are some of my favorites. Like mother, like daughter. Everyone does know that classes are female. Yes? Why? Because they reproduce parthenogenically. There is one parent, has many children. There's no mating. So they're all female. Now, basic biology people. You didn't know computer science crosses all of these domains.
So what if we get mixed-ins?
If we get mix-ins? Oh, that's a whole different topic. Yeah, and actually there's some fascinating diagrams to be drawn in that area, by the way.
Okay.
Child cannot demand more of colors than the parent. So another way to state that, preconditions cannot be strengthened in the child. So if you have a VI, and in your documentation, this is where this gets fun. You have to write documentation, and your people have to read the documentation. But if in the documentation you say, I accept all the numbers from 0 to 10 for this input, the child cannot say, I only accept 1 through 3, or some smaller subset. The preconditions cannot be stronger. If the parent class said, this is the range, then the child class has to say that's right. Now, the child can widen it. The child can say, I accept all integers, not just 0 through 10. That's legit. The child can do more, can be more accepting, but cannot be narrower. The child may over-deliver, but not under-deliver. Another way, post-conditions cannot be weakened in the child. So if at the end of this function, I guarantee that all of the data in this object is contained in a string, and it is sufficient, and that string is sufficient if I were to recapitulate the object, that has to be true. I can't have a legitimate child that outputs a string that is only some of the data. That violates Liskov. Now, there's some interesting use cases where those are useful. Alan created one for the debugging where he created a specialized serializer that would flatten the data but was lossy, threw away a lot of it, and produced a string that could feed into the debugger that was just this reduced set. But it couldn't close the loop and be deserialized because there wasn't enough information there to recreate the object. Now, that was useful to create for his debugger situation and to connect all the parts. But if he tried to then plug that class into a framework that was trying to do network communication, it would have fallen apart because it had weakened the post-condition that the parent had promised. If you find yourself fighting with too many of those, it's time to revisit your single responsibility principle and see if you can split responsibilities out.
We figured we were safe with the glossy serialization because we definitionally were never going to run deserialization. So nobody could ever go,
right.
No one could ever go the other way because that component wouldn't be dead.
Right, and so these things can change depending on how sure you are, business-wise, that these conditions will never be necessary. The child has to keep any promises made by the parent. Any invariance must be preserved in the child. The classic one is, whenever method X is called, I will increment this number in the database. It's a dynamic dispatch method. The child chooses to override, does whatever he does instead, fails to increment the database. That's an invariant that's been broken. The trick is, a lot of these invariants are only covered in the documentation. They can't be enshrined in code. Now, languages have done some things to try and help this over the years. Liskov did her work in the 1970s. She's still around. But we've taken some steps. So when you have the must call parent option in LabVIEW, it says when you override this, you must call the parent. That actually gives you an opportunity in our language to say, okay, I'm going to force you to maintain this invariant. I'm going to put some code up in the parent that you can't escape. And that gives you better control when you're writing your frameworks to make sure that children don't slip and because they just didn't read the documentation.
Template method helps too, right?
Templating method helps as well. This is my favorite. The child may only return errors that are returned by the parent. So, kind of, theoretically. You have a parent method, and let's say it says, I return error code 1, invalid argument, and error code 2, out of memory. And now you have a child that inherits, does some work on a file, and wants to be able to output error code 7, file not found. But I've got a caller. I'm over here, and I call your function, and I am reading your documentation. It says you can only return error codes 1 or 2. So I write my error handler to say, well, if it's error code 1, do this, and if it's error code 2, do that, and otherwise I assume that everything is fine, hunky-dory, and I write the rest of my code assuming you're going to succeed. Do you have a question?
Well, in the .NET world, they have errors as objects that can be inherited as well. So
but they still have to maintain this same invariant. I can come back at that one. Give me a sec. I wasn't necessarily going to dive in there, but I can loop it in. So I say this is the only 2 error codes you can possibly return. The child class inheriting, well, I need to return error code 7. This is where whoever writes your parent class has to be a little bit oracular. They have to look ahead and say, I am going to document that I can return error codes 1, 2, or 7. Even though I never myself actually return 7, I have to document that as part of my API in order to give my children permission to return error code 7. Error codes are notorious places for Liskov to be violated, and they can cause a lot of headaches downstream. Now, you were talking about exceptions, which we see in C++, C#, Java, where you throw an exception, and the caller then has to catch the exception. And you can create some specializations. And so this guy says, I throw exception. And as long as he says, I throw any exception, then you can use the full power of any of these error codes. But it's the same as documenting a terminal can return all possible errors. That's not necessarily helpful to the caller of that API. You guys get mad at me because there are APIs in LabVIEW that I won't tell you all of the errors that they return. It can return all of the error codes, and you have to be prepared for that. And you're like, why? And it's because I'm not going to narrow the scope of what we empower the different overrides to do. And most of the functions in C++, Java, and C# are stated as, I can throw anything. And so you have to be prepared to catch anything. The Java actually tried with its throws statement to say on every individual function, I'm going to document as a compiler-checked thing, this is the list of exceptions that this thing throws. And they actually, Java 1 spec says, you declare the function, throws A, B, C. Can't throw anything else. And then if a child overrides, the compiler will break them if they try to compile and try to throw anything else. And then the caller, if he doesn't catch A, B, and C, he has to put throws A, B, and C on him in order to document it. What that turned out to be was a disaster, because if they changed an API that said, well, actually, we need to throw Z in as well, then we modify throws A, B, C, Z, and that suddenly meant the caller is now broken because they don't handle all of it, so they had to either catch or amend, and it was a huge binary breaking disaster. So Java still has the ability to tag methods, but most people don't use it. And in much the same way, I document important error codes coming out of my functions. You should be aware of this one. This is a special case. This one occurs frequently. But I'm not going to say that that's the entire set, except on the most narrowly defined primitive functions, that this is it. Those low-level primitives, we hold. And there's been some times in LabVIEW where we've continued to return error code 1, even though we would love to return a different error code, because we weren't confident. It was such a frequently used function, we weren't confident that code would be resilient against a new error code.
Somebody would be expecting.
Someone would be expecting that error code and no other. And if we suddenly started returning a different code, they're going to go off the rails. That's the sort of very subtle break promises that is very hard to keep in mind. And as you can see, Liskov's substitution principle starts applying when you start even just talking about stepping away from classes just to function versions. This version 1, this version 2. Version 2, does it maintain the same promises as version 1?
Scope.
The scope, the input control, all of this, it starts applying in much the same way. So that's Liskov. I'm not going to go into open close tonight, because it's a longer conversation. Questions about Liskov? All right.
Have you done, like, I'm sure that you have seen examples of all of these stuff on LabVIEW code, like I mentioned, the big cluster.
Mm-hmm.
So do you have, like, pictures of those, like, examples of those LabVIEW code where people are either violating the principle or getting really close to achieve it, although you said it's not possible to achieve it?
Work on his face. That answers the question.
Yeah, I can't post most of my customers' code. They wouldn't appreciate it. And our code is perfect.
Yeah, right. Yeah. Have you looked at the example? Where is that?
No, I try not to. I code with my eyes closed. Some of the diagrams look like it. Yes, no, nothing published. This is an ongoing conversation. This is something that, as I said, several people have tried to present this material, myself included. I'm not like trying to put myself on some pedestal here. Multiple of us tried to present this material, and we kind of fell on our faces. And last year's presentation that John and I did was the first one that we walked out of, and some of the other presenters were there when we said, I think we actually kind of got those through. This year we did 2 other principles. The feedback wasn't as good, so we're going to have to retry those in some form. The material was there, but it was still too high level, still too abstract. So we're still building some of that up. We need architects who are able to contribute some of this to start that conversation moving. So I've given you a presentation. If I would present this to most LabVIEW users, they'll probably follow it, but they're not necessarily absorbing it to the same degree. They're not, a lot of cases, they're not immediately able to think in their own code of an example where they had exactly that. Just because the breadth of code they've written isn't necessarily that broad, or they haven't haven't coded long enough to realize when they fell off a cliff. That's the hard thing about being an architect, is it's mostly the cliffs you fell off, not the, oh, I got close and realized and pulled back. So that's something that's going to have to develop over the next few years as we try to broaden the breadth of our architects and the skill set that is inherent in LabVIEW's community. It will come with time, but no, I don't have particular examples. What I have is so far the presentations that I've shown you. And we'll try to have this ongoing conversation over the next few years in forums and presentations and whatnot. Anyone else?
I have a question about the second principle you have there in terms of over versus under delivering.
Mm-hmm.
I feel like that could be a matter of interpretation on a number of promises made about whether you're satisfying it really, really well, or if you're actually...
You're correct. That's why the mathematical stated version is the more precise. The larger size is the more general, trying to understand what that means. And basically, if it said it's true at the end of the function, it must be true at the end of the function.
Okay, so they do sort of a set theory on truth.
Yeah, that was how Liskov first formulated a lot of this, and how it has been expanded in the time since her initial work, to get us to the point of understanding, where these promises come from, what creates these promises, and that sort of thing.
A Google search produces a lot of things, but none of them are split. What would I Google, or?
For the 5?
Yeah.
Oh, yeah, S solid. Wikipedia solid entry.
Oh, solid. Okay.
Yeah.
Yeah, and I guess we'll put a link to it too on the page. You have access to the LabVIEW Architects Forum?
Yeah.
Yeah. So I'll
It's in here somewhere.
There it is.
All right. So single responsibility, do one thing, do it well. Open cross principle, try to build your stuff so that you have plugins, so you don't have to rewrite the stuff that you already know and have tested works.
Liskov substitution principle, keep your promises when you try to substitute one API for another. Interface segregation, try to break, even when you build one thing that is single responsibility principle, expose only pieces of that one thing to clients who don't need the whole thing. And dependency inversion principle, depend as much as possible on abstract ideas, not on concrete entities. That makes it easier to switch which concrete entities you're actually using at runtime. A lot of you who've ever written to have hot swappable hardware, one vendor for another vendor, have gotten into some of this, but there's intricacies to that last one that is far beyond what we're going to present here.
Robert Martin's book that covers these is really excellent.
Yes, I do
Yeah,
want to
Joe,
mention that.
yeah.
It's at the end here.
That's a very good book.
Worth your time.
There you go.
$160 to order it.
Agile software development. Many of you will be in places that scorn agile development. There are pros and cons to that, and
Yeah, forget about it.
you should know what agile is. You should be aware of why people champion it. You may or may not decide that you're someone who follows it. But as part of laying out agile software development, a lot of this stuff gets covered as, this is what makes good software engineering, thus, this is the process that achieves good software engineering. So the two are kind of related.
There's like two chapters in that book on agile project management, and the rest of it is software technique.
Yeah.
And the software technique is going to be applicable regardless of what your management imposes on.
And Dimitri has used it on his presentations, and he even says that he has read it several times because he finds something new. I remember when I did the unit testing presentation, that he was telling me some things that I was saying that he didn't agree with, and then he went and read the book, and he's like, oh,
Right.
you're agreeing with.
So I don't actually have a copy of Uncle Bob. That's what it's called. It's Uncle Bob's book. All software textbooks get slang named. The Dragon Book, that's what covers compiler theory for most of us. The various, the Tiger Book, that's the Java one. Anyway,
What's the design title?
the Gang of Four.
Okay.
Yeah. So the famous ones tend to acquire nicknames. There are various things that you may want to study that go further. If you're still, not quite on your feet with regards to object-oriented programming, we have a number of hands-on tutorials that are available. I happen to have printout manuals of them, but they're available online through National Instruments to kind of bring you up to speed. I encourage you to look at them. Active Framework, we've got a hands-on for that. There's also a course. But if you're looking for more...
Courses in beta, orderable through system engineering and custom engineering. Hopefully we'll get a part number in Q1. We'll see if that happens.
Cool. If you're looking for something more meaty to start getting into, this is my favorite book for learning object-oriented programming, called The Object-Oriented Thought Process. It's very small. The examples are obviously in text language, not LabVIEW, and he uses both Java and .NET. It's very well written without getting into details of a lot of syntax. And I've contacted the author. He has no problems if we were to publish a set of LabVIEW examples that go with each of his other pieces, if someone who's going through it actually generates that content. I've never gotten around to doing that. This is one of the finest books on LabVIEW itself that I've ever seen written. This is a software engineering approach to LabVIEW, John Conway and Steve Watts from England. Half of this book, the first half, is writing software, good software, how to design it, lay it out. The back half is software process. Here's how to handle source code control. Here's how to do a buddy session. Here's why to do a buddy session. Here's how to talk to your manager to convince them that pair programming is a good idea. Anyway, the front half is surprisingly undated for a book written in 2003 because he covered very broad principles. And while some of it is, I would love to see a reissue of it that actually covers LabVIEW classes because they can actually encapsulate some of the things that he believes as good disciplined programmers will organize their code like this. You can learn a lot just by going through this thing.
Expensive book for its size.
It is. All books on LabVIEW are expensive because they get color graphics.
Well, and actually in that one, it's printed on demand. So if you go to Amazon, it has pretty poor reviews, but it's because the publisher, because they went printed on demand,
The
the
print
pictures
quality.
are pixelated.
Yeah. So they are legible, but it is trickier. This is the aforementioned Gang of Four book. There's a website on ni.com where we have been slowly translating a lot of these into LabVIEW to kind of give people example code. The big major patterns, a lot of them have been translated across. This is the Software Engineering Bible, and for a book from the 1990s to still be in its 4th edition today, largely unchanged, is awesome. This is generated by studying a huge number of projects that succeeded or failed, and figuring out what were the patterns in all of the successful projects that the failures didn't follow, and extrapolating those out and saying, if you need to design a system like this, you probably need the following moving parts. We don't know exactly what you'll need for them in detail, but you're going to need something like them. And if you don't see something like them in your system, you might have a looming bug. This is Bloom's book, Peter Bloom, Bloomy Software. This is a LabVIEW style book. It's very well-written text, goes into a lot of detail as far as just good G code. It's low-level functions. It's not high-level architecture. He doesn't really touch a whole lot on organizing libraries, on preparing installers, on organizing larger-scale code modules. It's very much tactical, not strategic. Some of these others here are more strategic level. There's various other books out there that I can point you towards. Tom Bress is a brand new one that I helped review that I like as a, it's written for the lone wolf programmer very specifically as a, you are by yourself, here is a tutorial manual that you can go through in, I think it's 400 pages, but if you take your time and work your way through it like a lesson a day sort of thing, you can build up a lot more LabVIEW skill. So I brought these down because people frequently ask me where they can go for more info, and those are the ones that I point people towards these days.
My favorite part of the Gang of Four book is actually in the preface to the introduction.
Mm-hmm.
Their inspiration for the design pattern is not a software thing.
Oh, yeah.
It's actually structural architecture.
Yes, the term design patterns came out in the 1970s.
Because they were looking at urban planners, they were looking at people who design buildings, and the people who design buildings have certain solutions for certain kinds of problems, which are based on the fact that human beings are in a certain range and are capable of doing certain things. And from that, they realized that they could apply that to software. And personally, I use that to smack people upside the head when they tell me that I have to have a requirements document because you wouldn't build a building with a blueprint. We don't do construction. Software authors don't do construction, we do design.
Mm-hmm. And, yeah, and then you get a team of developers to actually write it down.
The team of developers is still doing design. It's still back and forth.
It is.
The only construction is done by the compiler.
So, any other questions?
Thank you for being good troopers.
All right. I hope I didn't overload you guys. Thanks for coming.
Thank you for the questions.